Good evening, everyone, and welcome to another vBrownBag webinar. Tonight, we are going to be continuing our Certified Kubernetes series, covering the major domains of the exam. And we're going to be talking with David Espejo about storage configuration and that domain of the exam. You may remember David. He was the first one to kick off our CKA series here on cluster architecture. If you have not seen that episode, I highly encourage you to take the time to watch it. It was an excellent overview, not just the CKA exam, but also of the components of the Kubernetes cluster and architecture. And give me a moment. I just realized that I was not sharing my screen again. So we do when we do it live. So yes, it was an excellent overview. So highly encourage you to go check out that YouTube video. It's up on YouTube. This will be up on YouTube as well in a few days. And just as a reminder here, we are on episode 7. So the other previous episodes are also on YouTube. We've had some excellent speakers so far. So please, take the time if you're interested in the CKA to go watch them. They were all very excellent. Few housekeeping notes, as always. You can get in on the conversation either live through this webinar by asking questions in the Q&A panel, or you can tweet them at vBrownBag, and we will try to get them answered by David on the air. You can follow David at David Mirror on Twitter. You can follow myself at Cloud Osmotic, and yeah. With that, David, I will hand the ball to you.
Great. Thank you so much, Sean, and welcome everyone again to our episode 7 of the CKA series. Now covering the storage portion of the exam. It's not the biggest one by any means. I mean, for the actual exam, the bigger topics are cluster architecture and troubleshooting. But even when storage plays an important role, probably not the most relevant role, but for the exam, you really need to know the life cycle of data inside a Kubernetes cluster, right? We will touch on different parts of kind of tips for the exam in terms of the scope of the exam, not actual questions of the exam. And well, without any further ado, let's get started. So as I was mentioning, it's just 10% of the whole curriculum, but you need to understand, right? Pay attention. That is 3 times. You need to understand these different objects and how do they work and how to use them, right? So this session probably won't be that long, really long, no, but we'll try to provide a baseline of understanding of these concepts, how they relate with each other, and then you'll have to make sure that you have the proper time to practice, to have hands-on exposure to Kubernetes. Right, so first things first, and the problem. What is the issue here? What is the challenge that Kubernetes has in regards to data? Because storage seems to be a pretty much solved problem, at least in the enterprise environment. We have, I don't know, different kinds of storage. You just put a block storage system, I don't know, storage array, hyperconverged infrastructure, whatever, and you get persistent storage for your virtual machines, and that's it. So what's the problem on Kubernetes? Well, the thing is that, remember that Kubernetes was created inside a public cloud provider, Google, and it has some implications. So we can figure out that with this example. We have an application set of pods. We can now speak about pods. Remember that pods are the fundamental computing unit in Kubernetes. So we have an application layer made up of, I don't know, 2 pods. And this application layer, it's needs to communicate and to interact with another pod that happens to be a database. Yeah, you can put a database in a container. It has some restrictions and all of that, but it certainly works. But for whatever you put in a pod, in a Kubernetes pod, by default, the behavior will be that the data is local. And if for whatever reason that pod is terminated, destroyed, deleted, the data that was there, it's also lost, right? So in summary, the life cycle of the data that pod in Kubernetes creates, it's completely tied to the life cycle of the pod, right? Data life cycle is tied to the pod life cycle, and that's a problem because pods are meant to be short-lived, right? The infamous cattle versus pets issue. Here, pods are certainly, well, cattle, and you just declare what you need from the infrastructure, and you don't care what's the specific pod ID that is doing it, right? So having the data inside this same short-lived, fragile life cycle, it's very problematic for many kinds of applications. So by default, in summary, the main issue, the main challenge is that there is no data persistence, at least not out of the box on Kubernetes, right? And this is a problem also that many of the container runtimes share. For example, Docker. By default, Docker doesn't do any form of data persistency. So there are many ways to tackle this problem. And that's the evolution of the what we have called the Kubernetes data model. So back in the days, like after Kubernetes or where Borg was donated to the CNCF and Kubernetes as we know it started to grow, one of the first mechanisms to try to have a method to create a storage for pod was to have static provisioning. What is static provisioning? Well, it looks like some of the tasks we in the past as vSphere administrators have been needed to do, to create, for example, create manually a volume or a set of volumes and then put virtual machines inside of those volumes. So it's kind of the same. You're creating, an administrator needs to go to the Kubernetes cluster and manually create volumes and the underlying, whatever is the underlying platform, and to also manually attach the pods to that set of volumes. So it was the first step on trying to have a mechanism for storage provisioning, but you can only imagine how problematic it could be. It's not that scalable, not exactly as the scale of, for example, public cloud providers. So next step was to have dynamic provisioning. We need to say that Kubernetes still supports static provisioning, and there are specific corner cases when we need to use static provisioning, and when we will see it here in the session. But next step was dynamic provisioning. Let's establish a way. The Kubernetes community established a working group or a special interest group, a group of people from different vendors, different backgrounds, to try to think about Kubernetes data model. So the first thing they realized was that, okay, this is a problem bigger than us, and we are trying to reinvent the wheel, right? There are a whole set of companies with decades of history doing storage. Let's give them the ability to create plugins. Let's create a plugin ecosystem on which many different storage vendors can create, again, plugins, and Kubernetes can use those plugins and attach workloads to it. Sounds great, sounds like a plan. The thing is that the model back in the days was or required that the storage vendor X, if they wanted to create a plugin and they got accepted to have a plugin for Kubernetes, they needed to basically check in code to the public Kubernetes repository. And that's the first problem, because if you're a vendor and you're checking code to the Kubernetes repo, you need to make your source code public. That's the first problem. The second problem is that many times it happened in the past that a Kubernetes release was blocked because a specific storage plugin from a third party, from a vendor, was not working properly with the new Kubernetes version. So that was the second set of problems. And finally, think that you're integrating third-party code into the Kubernetes core could cause that a bug in the volume plugin or the storage plugin could crash critical Kubernetes components, not only the storage plugin, right? So it was really problematic. That was called the in-tree model. And it's deprecated. The storage interest group doesn't accept anymore any in-tree plugins. So a new model was defined that is called the out-of-tree mechanism, on which well, the actual code or the actual implementation for the storage communication, the storage mechanisms, is outside the Kubernetes core, right? But it has two steps until we really can get there, right? So the next step to try to take that code outside the Kubernetes core was the flex volume. Flex volume still exists. It's been here for almost 2 years, more than 2 years. It still exists, but it's still maintained, but there are no features, there are no new features developed for flex volume. And the main problem is that for flex volume to work, we need to install a driver on each one of the host nodes or each one of the worker nodes where you're going to run your containers, and you will need root access on each one of those nodes to be able to install the driver file. So that's really problematic, especially if you are, for example, if you have a hosted or managed Kubernetes service, you probably don't have that kind of access. So that's problematic, but that was the first step to try to move the code outside the core. And the actual solution and what is considered the future for storage on Kubernetes is called the CSI, Container Storage Interface. It's an spec. It's a model or a specification by which every one of the vendors out there who want to provide persistent storage for Kubernetes need to abide by the standard, and all the implementation, all the details of that lives outside the Kubernetes core. So it's interesting because it's implemented using Kubernetes primitives, like, for example, pods and all of that. We will see it in the demo. But the actual details of how it's done or anything that happens with that specific CSI driver lives outside the core components of the Kubernetes cluster. So it may crash, it won't crash the whole cluster. And also it can be upgraded or updated to new versions without needing to affect compatibility with some other components in the Kubernetes cluster. So that's the not easy task that the storage interest group has been able to address throughout these years to finally decouple completely the storage implementation from the Kubernetes code itself. Right now, there's even a VMware employee is one of the co-chairs of that group. If you want to know more about what they are doing right now and what the future looks like, we'll make sure to put the link for the storage interest group for Kubernetes in the recording maybe, or if I can find some time, I will share it here in the chat later on. Right, so that's basically the story so far, from early beginnings to finally having a model that is scalable, and it lets every vendor to put his, to abide by the standard, but also put in, special features that set them apart from other solutions, and still not affecting Kubernetes itself. Right, so okay, the first of the objects or resources we need to consider here for the current Kubernetes storage model is what is called the storage class. What is storage class? I try to find analogies to vSphere. I hope you don't mind I'm doing this, but I know that most of the audience here is aware of vSphere primitives. So, and I was also a vSphere administrator back in the day. So for me, a storage class is like a storage policy, like a vSphere storage policy. I don't know if that's still a thing, or now the SPVM, storage policy based management. It's something like that. It's storage policy. It's not an object where you store files. No, it's just a way to declare this is one of the capabilities of that storage backend, right? As in a vSphere storage profile, or profile, I believe it was. We said what was, I don't know, gold, silver, bronze, I believe, and it depended on the performance tier, right? Or capacity, or I don't know, different set of parameters. So it's kind of the same here with the storage class. It's a way to declare different capabilities from a common backend or common platform, right? So you have the underlying platform. It could be virtualization, a local cloud, public cloud, bare metal, whatever. That's not the point here. The point is that the dev or ops or DevOps team will declare different capabilities this platform is able to provide. So this is the actual skeleton of a storage class. You will always have to call out the API version. One of the outcomes of the most recent KubeCon North America last week was that for some objects, the API version name will become shorter, but well, not that important, but you need to always start by calling the specific API version or API group. You will declare that this is storage class, you will assign a name, but the first thing you need to provide here as a parameter is the provisioner. So you will have not only probably not only one platform, but you can have different platforms. I don't know, the local cloud, the public cloud, whatever. So you will have provisioners for each one of those platforms. Where you can find the provisioners, let me share this with you. There you go. Here in the Kubernetes documentation, which let me remind you again that you can open up this website during the exam, and you're also allowed to use your bookmarks. So I have some pages still bookmarked, right? So you can use your bookmarks to move quickly in the Kubernetes documentation site. So provisioners, what kind of provisioners can we use? Well, everything's here, right? Public cloud, OpenStack base, storage, iSCSI, NFS, vSphere volume this is basically a BMFS data store that is created by Kubernetes, Scale.io, Storage OS, or the most basic one that is local. So that is basically creating a folder on your local machine if you're running Kubernetes locally. That is what I will do here in the demo, because I don't have yet access to a platform where I can do any of this. But here's the current set of provisioners that Kubernetes is able to use. So that's the first option you can set on the storage class. Here you will find, for example, Elastic Block Storage from AWS. And also below the provisioner, you will find the parameters for the specific provisioner. So each one of the provisioners has different parameters. So for example, EBS has the type of disk, but Google Compute Engine has a different set of parameters, Gluster, etc., right? So you need to check with your provider what parameters are supported. In case of vSphere, vSphere already has a CSI compliant driver. Remember, the CSI is the current status and the future, the state of the art for storage lifecycle on Kubernetes. And but VMware started this back in the days, so they even had an in-tree provisioner, but it's now deprecated for the reasons that I mentioned. So that's the second option, parameters for the specific provisioner. And then you will have the reclaim policy. This one is interesting because you could have different, you may have different reclaim policies for the same type of provisioner. What is a reclaim policy? What are the options? I don't know if it's here, but I'll tell you that reclaim policy has two specific options. You will have delete or retain. So what does this mean? I mentioned at the beginning that by default, the life cycle of the pod is tied, or the life cycle of the data is tied to the life cycle of the pod. So you could define a storage class that still has the same behavior, right? If you need to organize the capabilities your platform is able to do, but you have a specific set of containerized applications that are stateless. Stateless means that they don't save any form of persistent data. Like, for example, web servers, sorry. So you could establish a storage class or define a storage class that whose reclaim policy is to delete. So what will happen is when there is no one consuming, there is no volume consuming this storage class, there is no application consuming this storage class, or there is no application consuming the volumes that are tied to the storage class. I will explain better on that further in the session. Well, those volumes will be deleted also. That's the default behavior. But if you establish retain as the reclaim policy, whenever the pods are deleted, the volumes will remain live, will remain available, right? Because you set the policy to retain data, even when pods are deleted. So that's the meaning of the reclaim policy. If remember that if you don't specify any reclaim policy, it will default to delete. So you need to make sure that if you have stateful applications, you set the storage class to retain data, right? How to connect storage class to specific application, we will see it in a little bit.
And to be clear, so if a storage class is set to delete, then my pod spins up. I'm using a storage class. I'm using a backend data store. When that pod goes away, the data store goes away as well. So all files, all data in that data store is wiped.
Yeah, if we are speaking about, or we are referring to dynamic provisioning, which vSphere is able to do, yeah, the also data store will be wiped off.
Okay.
Right, the whole goal of these CSI drivers is to be able to handle the whole life cycle. We are speaking more about provisioning here, but also the idea is to for them to manage the decommissioning of storage also. Right, and also allow volume expansion. This is interesting because not, if you set that option to true, what it means is that whenever there is a volume created on using this storage class, those volumes will be able to expand live, to perform live expansion of, and also even file system expansion live. But not all the provisioners allow volume expansion, right? So from all this set of provisioners, only this short list allow volume expansion. Well, we don't have here one for specifically for vSphere. You can see here that we have one for CSI. So CSI is basically the standard, the umbrella standard. So it's right now on beta, but it will be soon available for any one of the CSI compliant drivers, the ability to live expand volumes, and obviously you cannot shrink them. It's so complicated to shrink storage live. So, but that's the ability to expand volumes. It's really simple to expand a volume if you have a provisioner that support that. You just need to edit the object. What object? I will show you in a little bit. You just need the object, and that's it. So that's basically the skeleton use of the skeleton of this storage class. It's a declaration of what a specific platform is capable to provide, and you can have as many storage classes as you need. Even for the same platform, from the same provisioner, you can have different storage classes, right? Okay, so that's the baseline. We are starting kind of from the bottom up. What's closer to the underlying platform? The storage class. So it's that all. Can we connect the pod to the storage class? Well, unfortunately, that's not the case. We need to have more logic for that. So that's the role of the persistent volume claim. So the persistent volume claim, the first step to connect the pod to an actual volume where to persist data. So the structure of the PVC is that, well, API, can metadata, specs, etc. You will have different access modes. So let me go here. There are some different access modes. Here, I will share with you in a little bit. The one you're seeing there in the example, which is read write once, well, will allow one writer or one pod to read and to perform read write operations anytime. But we have different access modes. Let me show you right here. Oh, there you go. Here we have the access mode. So as I mentioned, one node or one specific application, one pod can mount and perform read-write operations on that specific volume and with the read-write once access mode, right? But it's tied to a specific node, right? You can even have multiple pods consuming the same volume, but if they are running on the same node. So that's funny. Probably it works for lab environments, where you're able to to tie or yeah, to associate pods to nodes, but in a cloud environment or in a bigger environment, it's not that practical, right? So you will have also read-only many. It can be mounted and by many nodes, but it's read-only. And the most common mode is read-write many. So it's mounted by many nodes, and it also allows to do read-write operations. Right, so there in the CLI, it's interesting to remember this. We have abbreviations for each one of these modes. What's the role of this? If we are showing here a declarative way of creating a persistent volume claim, why the CLI? Well, there are two ways of doing things on Kubernetes, the declarative way and the imperative way. The declarative way is the more elegant, and it's the ideal for production environments where you have your YAML files, your Helm charts, your declarations for what you need in the infrastructure, and it's easier to maintain, easier to keep versions of this, all of that. That's great. But if you're in a rush, or if you are in a lab, or you are in the exam, it's useful sometimes to use the imperative mode, where you just go to the command line and you create the object right away without having to write YAML. The options are limited, right? You just cannot do all of this. Probably all of these options, yes, but for many resources out there on Kubernetes, not all the options can be created in an imperative way. So it's still necessary to know your YAML, know how to edit, how to troubleshoot your YAML files. But if you're in a rush and you need to create a read-write many, remember that it is RWX, right? That's the most common access mode for a volume on Kubernetes. Right, so that's the access mode. Also, the volume mode, resources request. This section, specifically here, the resources, is where you will request a specific capacity. So remember, we have an underlying platform where we have a set of storage classes, but we have never declared here a specific available capacity. Right, so the PVC is the place where you will actually request a specific capacity or space from the underlying platform. What if there is no available space? Where there are different mechanisms, but in the end, the pod will not be able to be scheduled, and the actual error message will be, well, probably there's not enough space on the underlying subsystem. So I've never seen an error like that, right? And we don't have here in Kubernetes something, at least not by default. Probably in the vSphere CSI provisioner, I remember that we have the theme provisioning, tick provisioning feature, but by default here, everything will be like theme provisioning, right? So here you will request a specific amount of storage. And also you have the option to, or you have here the ability to call out a specific storage class, right? So you're connecting, the storage class we actually created here with a actual persistent volume claim or a request from the dev team for a specific application. Requesting an amount of storage and attaching it to a specific quality or specific capability that the platform has with the storage class. Right, so that's kind of the connector between the pods. A pod doesn't call out a storage class, but it certainly can call a persistent volume claim. And at the end, in the end, what what all this process produces is persistent volumes, right? The whole goal of this is to have a place for pods to actually write data and save data. And those are persistent volumes. As we mentioned, providers are a long list of providers, including vSphere, Azure, all the hyperscalers. And for persistent volumes themselves, we talk about dynamic or static provisioning. Remember that, well, not all of the provisioners support dynamic provisioning. I have it, let me go here. I have a list of the volumes that support dynamic provisioning, but not all of them support it. Let me share dynamic volume provisioning. Here it is. Here you go. Yeah, like that. Using it. Well, meanwhile, is there any question out there?
So is there a way
No?
built into Kubernetes to, so like you can have network policies. Is there any sort of native way in Kubernetes to securely restrict certain pods or nodes from reaching a specific storage class? So I can call the storage class in my YAML file. What if I'm a developer and I don't want that developer to be able to access super sensitive storage class, right? Like, is there a way built into Kubernetes? Do you have to do that outside of Kubernetes with just, policies and things like that that you're aware of?
Yeah, I need to think about this. I'm not sure exactly how to do it. I'm sure that it's perfectly possible. I'm thinking if, well, I'm not sure how to do it, but certainly I can research that better, how to actually restrict. I understand the use case. Yeah, if you have a very limited resources tier of your storage subsystem, well, you certainly want to protect that. So there is a protection mechanism to prevent that someone accidentally deletes a volume that is being used by a pod. That is something different. But for actually preventing someone to use a specific storage class, I need to research on how to do it because I haven't seen that.
Okay. And then another question I have is, so you create the storage class and that's where you assign the provisioner saying, okay, if somebody requests this storage, if somebody requests a persistent volume claim with this storage class, the provisioner is a binary on the back end or some sort of automation on the back end that connects to the cloud APIs to provision an EBS disk or an Azure disk or something like to that effect. Do we also have to define persistent volume in YAML?
Not always. It's a great question. We will touch a little bit on that, but not always. Most of the times you don't need to do it.
Okay.
But yeah, we'll touch on that. Well, I can find list, but yeah, well, not all the provisioners support this dynamic provisioning. It's unbelievable that I lose it, but yeah, well, I will try to get it by the end of the session. So let's keep on moving. Yeah. Sorry. Well, okay. Let's keep on moving. So if your provisioner supports dynamic provisioning, we will see in the next slide what it means actually. Also binding, the default behavior for a persistent volume is that once it's created, be it dynamically or static, and if it matches to a storage class or to a specific persistent volume claim, the connection or the binding will be immediate, right? The term here is not to mount, because we mount data stores. And here the term is binding, right? When you bind a persistent volume to a pod, you can also specify mount options. For example, I will mount it in this specific path in the actual container host operating system, right? But in general, the operation it's a binding, and it could happen immediately. That's the default behavior. Or you can assign an option that we will use here in the demo that is called wait for first consumer. It's really interesting. Not all of the provisioners support that, and I know this by heart. It's only the three main cloud providers, only AWS, Azure, and GCP support this option to wait for first consumer, which is great because even if you have the persistent volume created, even if you have a matching storage class or a PVC, if you don't have a pod that is requesting that, it will not, the binding will not happen. So that's great because you avoid situations with, for example, a binding already happened and there's another application that needed the same, and the binding is exclusive, right? So if you wait for first consumer, you will ensure that only pods that are actually requesting the volume and are releasing it when they don't need it are the actual pods that will receive the persistent volume. It's interesting. It's not exactly a corner case, but it's not the day-to-day basis kind of behavior, but it's an interesting feature to talk about. What you have always by default with the binding is the in-use protection mechanism, which, as I mentioned, depending on the access mode, if you have, for example, read-write once, right, or a specific set of pods already bind to a volume, no one else will be able to delete that volume unless you delete all the pods, the deployment, and all the applications that are consuming the volume. But besides that, no one will be able to delete the volume. So that's important. The reclaim policy, also, if you're creating the persistent volume by hand, when do you need to create it? Well, if your provisioner doesn't support dynamic provisioning, for example, the local provisioner, if you're running Kubernetes locally, you need to create your persistent volume by hand, right? And you will need to establish a reclaim policy and all of that. And also you can specify options on volume expansion for the persistent volumes. If you remember, we have this in the storage class, right? So what's the point of doing this? If you define those features in the storage class, if you have a persistent volume claim that matches the storage class, and if your underlying platform supports that, you don't need to create persistent volumes. You don't need to specify anything of this. It will happen automatically, right? So I will try in this slide to connect the dots, right? Because I know there are several moving parts here. Not all of them have an analogy or a direct analogy to, for example, to a virtualized environment. So I'll try to join the dots here. So everything exists for the sake of the pods, right? The pods need a place to persist data. So the pods can call a persistent volume claim. We will see how it's done, right? So they call a persistent volume claim by the name of the persistent volume claim, and the pods define where to mount the eventual volume that they get, right? The persistent volume claim requests capabilities from a specific storage class, So remember that in the PVC YAML specification, we can introduce the storage class name. So we can call out a capability of the platform. The next thing that will happen is that the actual controller for this is going to ask a specific question to the API server. Does this storage class exist? Because if the PVC is able to call whatever storage class name it wants, it doesn't mean that the storage class actually exists, right? And if it doesn't exist, it's not magically created. Someone has to create it, right? The goal is that the Kubernetes administrator create the storage classes that the platform is able to provide, right? The capabilities that the platform is able to provide. So it will ask to the API server if the storage class actually exists. If the answer is yes, the persistent volume will be or creative if it supports dynamic provisioning, or it will be bound directly because it was already manually created by someone, but the end result is the same. The persistent volume will be bound to a pod and everyone is happy. But if the storage class doesn't exist yet, well, the API server will report pod status that is called pending. That's the pending status. And one of the most common reasons is it's calling a volume, or it's asking for a storage subsystem that is not created yet, right? So all this is the whole life cycle of the data in well, I don't know if for the data, but for the storage model and Kubernetes. This is how to connect all the dots or all the elements for an actual pod. It looks more complicated than it really is. Once we do it in the lab and once you do it, for all the practice you need to have for the exam, you will find that it's easy to understand, right? There's this hierarchy, these relationships between PVC storage class and finally a persistent volume that is or dynamically created or basically connected to the pod because already existed and matched the storage class. That's the summary. Up to now, any questions? No?
No questions from the group here. I think this is fantastic. This is one of the, seeing this slide helps connect the dots. So I think this is a great overview here.
Thank you. Yeah, because the troubleshooting section of the exam, which is everywhere, it's, the actual exam doesn't have a section called troubleshooting. Here's where the troubleshooting starts. Now, troubleshooting is everywhere in the exam. So it's important for us to understand. Remember that the curriculum asks that you understand. And this understanding will serve you during troubleshooting. If you find a pod in a pending status, probably you will start digging, okay, what's happening in the storage subsystem? Okay, there's a PVC, there's calling a storage class that doesn't exist. How to fix it? I will create the storage class. And that's it. So, problems are not that hard in the exam. I don't know. That's my experience, and I'm not an expert by any means on Kubernetes. So the main tenet for the exam is to actually understand the relationships between all the objects in Kubernetes. That's it. Okay. So to conclude here in this part of the session, so I find some analogies here with the vSphere environment. So I will say that a pod, well, it's like a VM. The PVC is what you actually have when you go to edit settings and you configure your VM to have any number of disks with any capacity, probably tied to different policy. What policy? It's kind of the storage class, right? This SPVM or this storage profile or whatever it's called right now. That will be kind of the storage class, right? And finally, for the storage class to actually exist and be something, it needs vCenter server, right? So the vCenter will be like the API server. And finally, it will result on a data store. Well, most of the times I don't remember that data stores are dynamically created because a VM requested, but I understand that vBols or any other integration can certainly do that. But well, the thing is, there are some analogies that could be done to finally understand all of this. Got it.
Yeah, that's great. Great analogies.
Okay. So let's move to the demo. Okay. Let me go here. And for this demo, I will actually use one of the coolest new features that we have now available is the ability to use Visual Studio Code on the browser. You just need to go to vscode.dev and open up a folder on your local machine, and that's it. You're ready to go. So we will use it to watch and edit some files here. So here we have an environment where we don't have anything created beside the basics. So it's an oh, sorry. It's an empty it's an empty cluster. So there's nothing in there beside the basics. Remember the core DNS, the etcd component for the control plane, the API server, control manager, basics, right? And we have something interesting. We have a provisioner, right? A local provisioner. So I actually created this, and but it, you know, depending on the implementation, you could have it by default. It depends. I actually created this, so it's the only provisioner that I'm able to use right now because of limitations. And but as you can see, it's running as a pod, right? And this is what I refer to, you know, dogfooding in Kubernetes. The CSI standard, the container storage interface, is actually runs somewhere else in your cluster as a pod, for example, or as a set of pods, but it doesn't run on the core Kubernetes system, right? It's not part of any of the control planes components. So this is a, you know, simple way to see the direction that Kubernetes is taking in terms of storage, right? So okay, we'll see. We don't have any storage class. Oh, we have one storage class, default storage class. So we have here some YAML already created. Let me use my new shiny visual code. We'll use this. Okay, there you go. It's a really simple storage class that is called local, and the provisioner for local storage is actually the no provisioner. It's nothing different than that. Remember that you can have many other provisioners, and I'm using the volume binding mode. Wait for first consumer. You can use that on local storage. So what it means is that even if I have a persistent volume that matches the storage class name, even if I request the same thing in a persistent volume plane, the binding will not happen. Not until I have a pod that requests all of this. So that's basically it. So I will create the storage class. Well, a side note for the exam, I'm using an alias for kubectl of kubectl, kubecontrol. Well, I'm using the Alice K, but you can certainly create some other aliases. For example, if you are going to run many kubectl get or kubectl apply, for example, I could do caf equals kubectl apply minus f, right? And I will say just caf storage class, and that's it, right? So it's important. It's one of the key skills during the exam to not waste time, to make the most intelligent use of your time. So aliases are really useful. So now we have a storage class called local with our no provisioner waiting for first consumer. Do we have any persistent volume? There is one created with a different storage class. It was already there, right? So looks like we have a persistent volume definition here. It's one that is called local volume. And here in the labels, you can use labels to start correlating objects in your Kubernetes environment, right? So if you have the web application, for example, in this case, I could use the label, the key value pair app web for, or tier web, for example, as a label, and also in the pod, you will use the same. If you use the same labels in the pod and in the persistent volume, will it cause that they bind? No. Now, the binding will not happen just because a label, but labels are important to organize your Kubernetes environment. And specifically for pods, they are useful, for example, to build high availability high availability mechanisms like replica sets or deployments and all of that, or services to expose pods to the external world. All of that uses labels. So, back in the days, the CK curriculum had the first skill of the CK curriculum 1 year ago was to be able to use labels and selectors. So it's important, the use of labels. Okay. And the actual spec for the persistent volume, the first thing we are calling here is the storage class name. It's called local. We have the storage class already created. That's great. We have it there. We are creating a persistent volume, which is 10 gig capacity. Remember that is read write once. It's tied to a single node. Well, I just have one node, get node. This is a single node cluster. I have everything running here. But for sure, in production environments and the public cloud, you will have several nodes. So probably you will need to use a different access mode for this. And also because this is a local volume, I will need to specify the host path. So this is the path in the actual host system, the actual host machine, where the data is going to be stored, right? So it's not recommended for any production environment for reasons that you can imagine. So, but this is only for demonstration purposes, right? Why do I have to create the persistent volume? Because the local provisioner doesn't support dynamic provisioning, right? So I could have a PVC matching the storage class name. I could have a pod requesting all of this, and still the pod will be unschedulable because there is no persistent volume created for this, and it won't be created until someone goes there to create it, right? So,
and when you create a provision volume without using a dynamic provisioner, does the access method have to match that of the storage or the persistent volume claim? The access.
Well, yeah, that's a good catch. Yeah, that's other of the parameters that need to match. And one of the most common reasons that you yeah, I remember a problem back then. I can't say that it was in the exam, but I remember that one of the reasons a pod was unschedulable in some other environment was that the access modes were different. The PVC was requesting a read write many, and the storage class was different. So in the exam, you don't need to overthink this. You just change the if the storage class has has precedence. So you will change the PVC and that's it. Um,
Okay.
so yeah, the access modes has to match. Good catch. Okay, so now we have persistent volume. There is local volume 10 gigs. It's available. Move this. It's available and it's using the local storage class. The status available means that no one is using it, right? It's not bound to anyone, right? So that will be the case. So remember in the storage class, the persistent volume in this case, we needed to create it by hand. And now we have the persistent volume claim, right? So the actual persistent volume claim will call the storage class name. We will have a match there. It will call the same access mode. That's great. And it will request 2 gigs of capacity, which is less than the actual persistent volume has. So another reason it could actually fail, it will show the error, it will show you the error right away during the PVC creation. It won't let you do it if you are requesting capacity in excess of the persistent volume. Right. So PVC it's requesting capacity. So we have PVC, vBrownBag. Okay, so we have the PVC and it's in status pending, right? So we go to the PV, it's still available. So nothing has happened right now because no one is using it. Remember that we said in the storage class feature called wait for first consumer. No one is requesting this. This is all storage, but there are no applications there. So we'll create a pod that actually consumes or that will complete the whole life cycle and we will see how it changes, right? So here we have the actual pod definition. In the spec, you can introduce a section called volumes. Here you will assign a name to the volume, right? It's now the volume that you are going to consume. And you will call the persistent volume claim, the PVC, right? Remember the diagram, the pod doesn't call, doesn't call persistent volume, it just call PVCs. So you will call the actual PVC that we already have. There is local PVC. And the actual containers will mount this volume in a path inside the container OS. So it's a tiny operating system and it will mount there the volume. So whenever this container puts data in there, it will end up being persisted, in this case, in my local machine. But if you're using Amazon or other providers, it will end up being persisted there, right? That's the actual workflow of the data. A mount path inside the container that calls a volume that actually comes from a PVC that also consumes a storage class and that finally connects to the platform. Right, so I will create the actual pod. Okay, so now that the persistent pod is created, we'll see the behavior of the PV. The PV is now bound, right? It's been used by a persistent volume claim that now it's not in pending status, but it's now bound. Right, so and now the pod is running. So whenever we put data in there, it will end up in the actual provisioner. So that is kind of the actual workflow of the storage component on Kubernetes. And as far as I remember, and as far as the curriculum goes, it's basically all you need to understand to be successful in this section in the exam. So I don't know if you have any other questions, comments.
Let me check here. Oops. No, it doesn't look like we have any other questions. This fantastic overview of storage, the storage domain, and again, really enjoyed that connecting the dots piece. I know when I was starting out understanding persistent volumes, persistent volume claims, storage classes, I would always get PVs and PVCs, well, and SCs confused. So I think this is a great overview here and excellent explanation. Thank you so much, David, for the presentation and the walkthrough, the live demo. That was an extra. That was a nice bonus to see that live. So.
Awesome. It's my pleasure, and I hope it's useful for folks out there preparing for the exam.
Appreciate it. Well, again, thank you so much to our guest tonight, David. Really appreciate you coming on. Thanks for everybody in the audience. And be sure to tune in next Wednesday for episode 8 and then following Wednesday for episode 9, where we wrap up the series. And with that, everybody have a great night. Talk to you later.
Yeah.